So we're through with all the formulas that are in chapter 5, but there are a lot of formulas there. So I have a flow chart on the board in order to help you determine when to use what formula before we go try some examples where everything's all mixed together. So the first question you ask yourself is, are you making a single or multiple deposits or payments? If you're only making a single deposit at the beginning, or you need money at the end, but you're only making a single deposit at the beginning, it's either a simple interest, a compound interest, or a continuous interest problem. And it will tell you that word. It'll say simple interest or compounded so much or compounded continuously. That's when you use those top three formulas. If you're making multiple deposits, the question becomes then, do you know the amount of the deposit, R, or do you need to figure out what R is? So you either know the periodic payment or you don't. If you know the periodic payment, the question becomes, do you need the money at the end or the money at the beginning? If you need the money at the end, it's a future value. If you need the money at the beginning, it's a present value. If you do not know those periodic payments or those multiple deposits, the question becomes the same. Is it the money at the end or the money at the beginning? If you need the money at the end, you're saving up for something, then it's a sinking fund. If you have the money at the beginning, such as a loan, when you have the money up front, then it's an amortization. And that should help you determine when to use what formula. So let's try some examples where we don't know right off the bat what section it came from or what formula to use, and see if we can make sense of this flow chart to get to the formula so we can find the correct answer. Okay, so this is example 3. And it says, suppose payments will be made for 6.5 years at the end of each semi-annual period into an ordinary annuity earning interest at the rate of 7.5% per year, compounded semi-annual. If the present value of the annuity is $35,000, what should the size of each payment be? Okay, so when I read this, I notice I'm making multiple payments. So I'm over here where I'm making multiple deposits or payments. And now I have to figure out, do I know what the payment is, or do I need to figure that out? So it says, what should be the size of the payment? Well, I'm trying to figure out what the size of the payment is. So I'm over here either in the sinking fund or an amortization problem. The question then becomes, do I need the money up front or do I need the money at the end? And it says if the present value is $35,000, that tells me that's the money up front. How much am I going to have in terms of each payment? I've now narrowed it down. So I need to know the size of the payment. I need the money at the beginning. That makes it an amortization problem. So example 3 is an amortization. Okay, and so we have, let's see, what do we need? We need P, make sure I use the right letter, P, which is equal to the 35,000. That's what I have up front. We know little r interest rate was 0.075. We know T is for 6.5 years, so 6.5. And we're doing, I think it's semi-annual, so M is equal to 2. So using the amortization formula, we get R is equal to 35,000. And then we have 0.075 divided by 2, all over 1 minus 1 plus 0.075 divided by 2. We're going to raise that to the negative 2 times 6.5 as an exponent. Then you just have to number crunch that through the calculator. And you should end up with $3,450.87. So if you borrowed $35,000 today and paid it back in semi-annual installments, you would owe $3,400 every 6 months for the 6.5 years to pay it off. Let's try another one. So our next example says that Jonathan is the owner of a computer consulting firm. He's currently planning to retire in 25 years and wishes to withdraw $800 a month from his retirement account for 30 years. At that time, how much must he contribute each month into the account, earning interest at the rate of 6% per year, compounded monthly, to meet his retirement goal? Okay, there's 2 different amounts of times listed here, so that means this is a definite 2-step problem. So we have the now, and we know he's going to make deposits for 25 years. Yeah, because he's going to retire in 25 years. He's then going to retire. And then he's going to withdraw from that account. And we know that he's going to need $800 a month at this point. He wants $800 a month, and that's for 30 years. At that point in time, there's going to be no money in the account because he's used it all. So zero. In other words, he's dead. Okay, so that's kind of a picture of what's going on. Let me get a couple more pieces of information on the board. We know that it's at 6%, and we're doing everything in terms of monthly. So little r is 0.06, and m is monthly. Okay, so we have to do two parts here. We can't start with this until we figure out how much he needs. So our first step, or the first part of this, is what he needs when he retires. So how much does he need when he retires? So I'm trying to figure out this point in time what the dollar amount is. Okay, well, we do know that it's periodic payments, and we know that those $800. We know that he's going to end with zero amount at the end, so we need the money up front. So we have the payment amount. We need the money now. That's a present value. So our very first step we're going to do is the present value of an annuity. So that's going to give us that P is equal to the $800. That's our R. Then we're going to have 1 minus 1 plus, and I'm just using the present value formula, 0.06 divided by 12. And again, he's going to do that for 30 years. So that would be negative 12 times 30 all over 0.06 divided by 12. That's how much he needs in the bank when he retires to be able to pull $800 a month out of it for those 30 years. And if you do that, you end up with $133,433.29. So that's how much he needs to save up. So that's his goal in terms of how much money in the bank. So that number is this number right here. So now we have to figure out if he's going to make periodic deposits for 25 years, how much does he have to put in every month to get to that? That's a sinking fund. We need the payment amount, and we know what our end goal is. So now we'll use the sinking fund. Okay, so R is equal to $133,433.29. And again, we're using the sinking fund formula. We have 0.06, it's still the same interest rate and still the 12 months, all over 1 plus 0.06 divided by 12. This time, my exponent is 12 times 25 because he's only saving up for 25 years, and then minus 1. And if you do that, you end up with $192.55. So if he deposits $192 every month for the next 25 years, then once he retires, the amount of interest is built up enough that he can then withdraw $800 a month for 30 years. And that's how much that interest is working for him. Of course, 6% is outrageous. You're not going to find any retirement accounts paying 6%, but it's a good illustration of why you want to save and save long term to be able to pull out long term when you retire. Okay, I have 2 more examples I'd like to go through really quick. And again, we're just summarizing all the different formulas and the different words and everything that we've seen. So this is example 5. Matthew secured a loan of $12,000 3 years ago from a bank for use towards his college expenses. The bank charged interest at the rate of 4% compounded monthly on his loan. Now that he's graduated from college, he wants to repay the loan by amortizing it through monthly payments over 10 years at that same interest rate. Find the size of the monthly payments he'll be required to make. So again, we have 2 things going on. So step 1 is he borrowed the money. He borrowed a lump sum 3 years ago. Okay, so he didn't borrow it in payments. He got the money up front. And because of that, that's a compound interest problem. So we need to figure out what it's now worth after 3 years. So we said he borrowed $12,000. 1 plus, and that was at 4% divided by 12. and for the 3 years. So 12 times 3. So in other words, he borrowed it 3 years ago. Now what is it worth that he has to pay back? And if you do that, you end up with $13,527.26. Okay, part 2 is now he's going to come back and repay that. So he's going to repay for 10 years. We need to figure out what R is. How much is he going to pay every month? So we need to find that periodic payment R. Okay, so this is the money up front. When he's done paying it off, he'll have 0 at the end. So that's an amortization formula. So R is equal to, using the amortization formula, 13,527.26. Then we're going to have 0.04 divided by 12. Notice the interest rate stays the same, still at 4%. 1 minus 1 plus 0.04 divided by 12. But it is for 10 years. So he's going to pay it back over a 10-year period. And if you number crunch that through, you should end up with $136.96. So the student loan is $136.96 every month for those 10 years until it's paid off. Okay, one more. Let's go do a car loan. When you go buy a car, a lot of times the dealers are offering rebates. So let's take a look at what that rebate does for you versus a 0% loan. So, final example says, Tiffany is considering the purchase of a new car. She's narrowed her search to 2 cars that are equally appealing. Car A costs $28,000. So this is car A. It's a $28,000 car. Car B is a little bit more expensive at $28,200. Okay, the manufacturer of car A is offering 0% financing for 48 months with 0 down, while the manufacturer of car B is offering a rebate of $2,000 that they then use as the down payment, basically. At the time of purchase, plus financing at 3% per year, compounded monthly for 48 months. So that would be T, with 0 down again. She's decided to purchase the car with the lower net cost to her. Let's figure out which one she should purchase. So we're going to do this one at a time. Let's do the easy one first. So if it's got no interest charge, it literally is just $28,000 divided by the 48 months. And that's how much she would pay per month. The dollar amount that she's going to borrow, that she's basically buying from the, or borrowing, I guess, from the dealership, divided by the monthly installments. And that comes out to be $583.33. Okay, now over here, she needs to borrow an amount from the bank. We need to figure out what the monthly payment is. That's an amortization again. So again, we're looking for R, the periodic payment. We need the money up front so that the balance at the end is 0. We do have to recognize that the $28,200, the $2,000 is taken off the top of that. So when she goes to the bank, she's only going to finance $26,200. Okay, so R is equal to that $26,200. I'm using the amortization formula. Again, I didn't write that down. Amortization. It's a low. So we're going to have our 0.03 divided by 12 all over 1 minus 1 plus 0.03 divided by 12 to the negative 12 times 4. Okay. And if you walk that one through your calculator, you should end up with a monthly payment of $579.92. So they're really close to each other. They're only off by less than $4. But this one is the lower one, because if she pays this over the 48 months, she'll end up paying less than if she pays this for the 48 months. So the better option is car B, the slightly more expensive car with an actual interest rate of 3%, but that $2,000 rebate is what's working for her. And that wraps up chapter 5 for